by to give a seminar. Normally, I don't give a long speech before seminar, but this talk deserves a few more words for our students, especially. I collected some information about Dr. Hog. Let me summarize it. Erik is responsible for many of the innovative techniques employed in the Hipparcos and Gaia missions. He proposed in 1975 a new design of a scanning astrometric mission, which became Hipparcos. In 1992, he proposed an astrometric mission with CCDs in time-delayed integration, which became Gaia. Erik published the following catalog with his colleagues in 2000, the Tycho II catalog of the 2.5 million brightest stars, which has been one of the most important catalogs in astronomy. Erik received the ESA Director of Science Medal for outstanding contribution to the science program in 1999. The International Astronomical Union gave the name Erik Hog to an asteroid. This drew a medal from Russia awarded in 2009. Although Erik has been formally retired, he is still contributing Gaia Mission with his papers. Erik's papers are kept and registered in the Royal Library near Copenhagen. Thank you, Erik, for being here with us. Let us listen.
Thank you for the very invitation to come here and for the nice welcome we have received. I should tell you that about half a year ago, when I was working on Gaia Mission in 20 years, I had saw a paper by Tansel and Selçuk about calibration of absolute magnitude. And I had some questions that I wrote to them, and I got immediate answer. Then there was something I did not understand because I don't know everything, so I had to ask, and they answered immediately. And also when there were further questions, they answered immediately. This is not so often that you get immediate, very useful answers from colleagues. I'm very grateful for that. And so I said to my wife a few months ago, don't you think this is the time we should go and see Istanbul? I was in Istanbul alone with a group 3 years ago, and I said, when I came home, we must go there to see all these things. So, and this is the time. So I wrote to Tansel and Selçuk if they would like to have a talk. And they immediately answered yes, and that's why I'm here. So I'm presenting you now Gaia Mission results and the prospects, a review I'll give. And it is divided like then I'm a question. I have not switched.
This must be.
But I can use this. Yes, now it comes. Yes, now it's okay. Thank you very much. So, first part is the Gaia mission and how it performs and the science you get from it. The next part are about long period exoplanets, how they can be determined by astrometry, detected by astrometry, and about a Gaia successor, which only ESA can do and which must fly in 20 to 30 years. That's what I'm working on. So first, about astrometry. Astrometry is about positions, proper motions, and parallaxes of stars to determine them to the best possible accuracy. And there is absolute astrometry, which means absolute astrometry of positions all over the sky connected in a good coordinate system. Then there is relative astrometry, which you can make in a telescope with a small field. Yeah? And all sky astrometry is really the all sky and the small field astrometry. So what I'm talking about today is only absolute all sky astrometry, not the other small field, which is also important, but not the subject of today. And absolute astrometry was done for 300 years, was done mainly by meridian circle. Here's a meridian circle, a telescope on a horizontal east-west axis, and you observe a star when it crosses the field of view, observe the transit time, and the inclination of the telescope gives a declination. That is meridian astrometry. But in 1989, we launched a satellite which could do absolute astrometry much more accurately. The Hipparcos satellite by ESA, which you see here. And in 2013, we launched the Gaia satellite, which you see here. And the question is then, what is the future for all sky astrometry? After Gaia, what must come after Gaia? That's what I'm working on. So a Gaia successor is needed by 2033. That's what I'm trying to convince you of. And the Gaia measurement principle is shown here. You see, here's the satellite, and the spin axis means that the two telescopes on board will observe stars on a great circle. Along the great circle, they will measure. And then the spin axis is turned a little all the time, so that the next circle will be a little bit tilted. And the measurements are done by the stars coming into the field, and in 20 seconds about, they go across the field. First they are measured astrometrically. First they are detected. All stars to 20th magnitude are detected and then measured in the remaining part of the field. And then they are measured photometrically and then spectroscopically the brighter ones. And the resolution is 1/10 of an arc second, which is comparable to the resolution of Hubble Space Telescope. It will map the entire sky with this detail to 20th magnitude, which means 1 billion stars. And here's the first image we got from Gaia in February 2014 of a globular cluster in the LMC. Just 3-second integration time of this small field gives all stars brighter than 22nd magnitude, in fact. And the spectroscopy is done on the calcium triplet in the near infrared, 27 nanometers, and you see spectra here of different spectral types. They'll be recorded for all stars to 15th magnitude. And this will give radial velocities for these stars and also spectral classification. Then here is a prediction of the accuracy. And let us just look at the 20th magnitude. The accuracy was expected to be about 300 micro arc second, which means less than 1 milliarc second. And in fact, there have been problems with stray light in the satellite. So the faintest stars will not get that high, but still better than 1 milliarc second. And milliarc second was in the thousandths of an arc second. And that was the accuracy obtained with the Hipparcos satellite, but only for stars brighter than 8th magnitude. Here, this accuracy will be obtained for at 20th magnitude. So it's an enormous improvement of performance compared with photometry, about 40 million magnitudes as these faint stars. And then I'm going to tell you historically, how did Gaia begin? In August '89, Hipparcos was launched, and we were all occupied with the data reduction, this enormous data reduction task, which was the largest data reduction in the history of astronomy by that time. And also, I was occupied with, I was leader of 2 data reduction consortia for ESA, one for Hipparcos data, another for Tycho data. But a visit to the Soviet Union in 1990 gave me an impulse. So during 2 years, I had dialogue with Russian colleagues in Russia and in Copenhagen, where we discussed what could be the next step after Hipparcos. And in '92, I was able to make a proposal which became Gaia, as I'll tell you. It was a scanning mission with CCDs. I called it Römer because Römer was the astronomer, Ole Römer, he discovered the finite velocity of light in 1676, and he invented the meridian circle. So it was a proper name to give to a mission, the Römer mission. And I introduced CCDs in the scanning mode, which CCDs have much higher efficiency than the photomultiplier tubes, which were used in Hipparcos. So that, and they could measure, as I'll show you. So, the next question, after Gaia, what then? Well, we'll return to that later on. But first, in the USSR, by '89, there were 3 proposed successors to Hipparcos. Lomonosov, one was called Regatta, Strong Ice. So they are really thinking about the successor. And their idea was that these, all 3 aimed for a launch, perhaps only one of them would be launched, but they worked on it before 1997. Then they could get from the second epoch of the Hipparcos stars, 100,000 Hipparcos stars go plan, if they get positions 10 years after, they would get very accurate proper motions. That was their idea. So get accurate proper motion for 100,000 Hipparcos stars. That was their aim. And by '89 in USA, they also had a plan for a successor to Hipparcos, called points, which was with the interferometry they wanted to make it. Now, in '91, we had a meeting in Copenhagen, and here are the 3 persons from Russia, and myself in my office at those times. And one of them, Erik Hog, stayed in Copenhagen from then on. He stayed in Copenhagen and worked with me for 7 years on the Tycho data analysis. Very bright boy. Now he went to the United States and is now at the US Naval Observatory, the big observatory for astrometry in the United States. And here is my ideas of Römer, the Römer satellite. September '92, stars come in here and they pass the CCDs, CCDs with elongated pixels because the resolution of the telescope is different in one direction and the other. So the diffraction image looks like this, and the size of the pixels in the CCD must be of the order of the core in order to utilize the resolution of the telescope to get the faintest stars as accurately as possible. That was foreseen. And the stars move across, and all the data are then accumulated as they move, and the reading is done here at read registers. And with 2 telescopes and a 5-year mission, astrometry to a 1/10 of a milliarc second could be done for all stars the 14th magnitude. And so that was the idea. And I reported in the partner science team, I reported about these things with, I asked if I could have 10 minutes to report, and our team leader, who was Michael Garriman, he was a bit hesitant to give me the time, because I couldn't understand why, because I thought it's so important that we look at the future. But later on he told me, well, his job was to get the data from Hipparchus down to Earth and get it reduced. It was not to plan a new mission, not by that time. But anyway, I worked on a new mission and got the 15 minutes. And in '93, I was able to collect the interest from these people, and we submitted a proposal for a medium-sized mission at ESA, which we called the Römer mission in '93. It is, for instance, Kovalevsky, you may know him. And yeah, well, let's go on. Here is how it looked, a satellite like this, with for the M3 mission. And it was submitted in May '93, and it was rated highly. In fact, the Astronomy Working Group rated this mission proposal as the best proposal of astrophysical proposals. But they said, better, do it 10 times better and get a cornerstone mission. So we thought that's a bit too much to get 10 times better accuracy. But in October, we were able to submit a proposal for such a mission, which should use interferometry. And we called it Gaia, which means global astrometry by interferometry for astrophysics, we called it. And we submitted a proposal for a cornerstone mission, either of a large Römer or the Gaia, as two options without a priori excluding either. A large Römer means just larger aperture than I had proposed, because if you're a larger aperture, you get higher accuracy. And it turned out, with the subsequent studies, that the interferometry was not a good idea. So actually, it became a large Römer, but it kept the name Gaia. But interferometry fascinated us all.
Okay.
Interferometry fascinated us in '93, also me, and I worked on astrometric design with interferometry. But only the innovation about higher accuracy has been retained in Gaia. Now, interferometry meant that there would be a telescope with two parts of the aperture of a big mirror open, and a secondary mirror and a tertiary mirror, and then so a long focal length, and then each image of a star would have diffraction patterns, which in principle promises high astrometric accuracy, because you have a small scale and you promise high accuracy. But how to detect them was not clear. So in '97, so now we are 4 years later, in fact, a cornerstone study was selected, but in a very interesting way, because, well, we had been interested in interferometry and proposed it. And in '97, the ESA committee selected space interferometry for a cornerstone study. Not space astrometry, but space interferometry. And one of the interferometry studies options proposed for space was the astrometry, Gaia. And so that should be studied first. That was the selection. But it means that perhaps without Gaia, there would have been no astrometry cornerstone in ESA. Could well be. So you see how very tight on the decisions are taken. It's a great risk to go into such things. But we have passed all the tests, so far it's been good. And in Germany, I proposed proposed an optical system which could be demagnified, much smaller. And the Germans took that idea up and studied a small interferometry option for 8 years, before they didn't get the money for it. And so they joined the Gaia project, which was good because without their experience and efforts, Gaia could not have been carried through. So, Gaia idea looked like this: 3 stacked interferometers, piezointerferometers. They have 18 mirrors and 3 focal planes of interferometry, which has very high stability of order nanometer and microsecond. And we could do that. Couldn't see it. But here's one interferometer, and the second here, and the third here, and then there will be a 4th telescope to determine radial velocities. That was the design in June '97 of Gaia. But the industry said, this is not a good idea. It would be better to have a large rover. And therefore, their proposal was big mirror 1 and secondary mirror looking in the 2 different directions, and then collecting the light on 1 focal plane. So that is in principle the Gaia as you see it, as it is flying now. And here you see the hardware which carries the mirrors. It is made by silicon carbide, which has very low thermal expansion, which is important because it must be very stable, and it is launched to the L2, to orbit around L2, so it's always in sunshine, constant temperature environment. And the focal plane here, stars come in here, are measured astrometrically, then photometry, and then spectra. That was how it looked in 2011. And let us see about astrometry, what accuracy you have on obtained in different years. From year 150 BC, Hipparchus astronomer, Ptolemy, and then Tycho Brahe, and then gradual improvement of the accuracy. You see here the scale of accuracy in logarithmic scale. And for 400 years, a gradual improvement of accuracy. Then came the jump in accuracy with the Hipparchus mission, a factor of 100, and then with Gaia would be another factor of 100. So that is what has been obtained in 2,000 years of astrometry. And now let us look at the Gaia data processing and release. The Gaia mission, there is a data processing center in Spain, ISAC. There are also other data reduction centers for Gaia, but I'll mention only this and tell that it has a storage capacity of 200 terabytes, and it can make 20 tera operations per second. 20,000 billion operations per second. That's what they could do in February this year. And the data release will be 2016, a catalog which will consist of positions and magnitudes for all stars, and they will only release those which have a single star behavior, not double stars will not be released because they cannot be well enough observed. And 100,000 prober motions, namely by the Hipparcos positions 25 years ago, and the Gaia positions, they give very accurate prober motions for these 100,000 stars. Now, let me explain. Parallaxes means distances to stars. And every star makes an ellipse on the sky. The smaller the distance, the larger is this ellipse. So in 1 year, the star will go around like this in an absolute coordinate system. And the proper motion will give a linear addition to the position so that this ellipse will be drawn out to a spiral. And it is the task of astrometry to distinguish the parallax from the proper motion, position component. And that requires at least 3 years of observations. But if you see here, if you know the proper motion of stars, then you can subtract the proper motion and then reconstruct the parallax by only half a year observation. And you know the proper motion for all the Tycho 2 stars, which is this catalog of 2.5 million stars, where we have determined the proper motions by means of 100 years ground-based observations and the Tycho observations. So they will make a catalog taking the proper motion from Tycho 2 and the observation of half a year from Gaia, and then reconstruct the parallax for all these stars. That will be taken as a kind of as a validation of the data reduction task. Perhaps it will be published, but depends on how good it is, so we'll see. And now we come to distances of stars. Hipparcos could determine, before Hipparcos, we knew only the accuracy of one star with a 1% accuracy, namely the sun, distance to the sun. But with Hipparcos data, we know at 1% accuracy for the distances to 719 stars. Gaia will give a 1% accuracy for the trigonometric distances for 10 million stars. So an enormous improvement. But still 80% of Gaia stars will have poor trigonometric distances. There will be larger errors than 20% for 80% of the stars. So it is needed to have photometric spectroscopic distances for all these stars. And that's what I'm working on now and where I've had help by your colleagues here. So, and these photometric distances are needed even more if we have a Gaia successor. Because then with Gaia successor we can get accurate proper motions of very distant stars. For mapping of the dark matter in the halo. And this photometric distance obtained by absolute magnitude, by an extinction and invariant magnitude from multicolor photometry and spectroscopy. That will give the photometric distances. Now here are some of the surveys by which it can be done. And we expect that for by now, we can give the distances for normal single stars with about 20% accuracy. This is appears from a study by Santiago from this year, based on calibration with Hipparcos parallaxes. But with the 1% accuracy for 10 million stars, which will be available in 5 years, or about, then better luminosities can be obtained for study of stellar structure and evolution. Theory, astrophysical theory can be improved. And better calibration of the absolute magnitude for much larger sample of stars. And a 3D map of the interstellar clouds can be obtained you can for every star, you know the distance, and then you can see in the spectrum whether there is a cloud, and then you have the distance to the cloud. So this means that we expect that by 2025, the distances for normal single stars can be obtained with 10% accuracy, given the photometry available by that time. So better by a factor of 2 than now. And a study by year from 2013 indicates that distances for giants can be obtained with 2% errors by 2025. Now I come to a Gaia successor in 20 years. What are the plans? Well, it should have a similar astrometric performance as Gaia, so that we have 2 epochs of positions. And from these 2 epochs, we can have proper motions for all these billion stars, 10 times smaller errors than from Gaia alone. And the parallaxes obtained would be quite a lot better, because the motions in binaries affect the determination of the parallax from a single mission. But if you have a very accurate proper motion, then you can disentangle these 2 effects. And there will be high resolution photometry with 140 milliarc second resolution, because the photometry in Gaia successor should be by filter photometry, as I will show you. See, here is the proposed Gaia successor. Here is sky mappers to detect the stars, then astrometric field, just as in the present Gaia. But then comes not the low resolution spectroscopy as in the present Gaia, but just filter photometry, which preserves the angular resolution, so you can have 3 or 4 colors, which is needed to have color photometry to reduce the astrometry. So Gaia successor in 20 years. And here's now one example of the expected science from such a mission. Just one example, I'll give others later on. Long period exoplanets can be detected only by astrometry in large numbers. Here is the 925 known exoplanets in 2013. And here I have shown 10-year period, 20 years, 40 years, so in this interval, very few are known. All these are obtained by radial velocities and by Kepler transit method, but they cannot reach this period interval, 10 to 40 years. And so far, none of them have been determined by astrometry, but Gaia will give thousands of them with periods up to 10 years. But 2 missions will give the following. I've illustrated it here on a circular orbit. Just to take an example of a circular orbit, you will have 5 years of positions from Gaia, and then from the second Gaia mission from 20 to 25 years. So these pieces you will obtain. And from the Parcos mission, you have 3 years. So you see, since the 2 missions would be able to collect these to one orbit, because the proper motions will be determined. So you can see one orbit of 30 years will be reasonably well covered. And if you look at a 12-year period with the same kind of observations, you will have it very well determined. So you can determine from such 2 missions exoplanets with much longer period than by any other method, for thousands of them. And planetary systems, why is that important? Let me explain. Some long period planets, formed in the outer part of the system, they migrate, they are formed beyond the snow line, where Jupiter, Saturn, and so on are situated, and they will migrate inwards. That's known, they will. But how many will do it? How many will migrate? We don't know. How heavy are they with migrate? We don't know. And what effect does it have on the habitable planets, which have about 1 year period? We don't know. Because all these theories of migration have no observational basis, only theoretical. We don't know about the planets before or during their migration, but the Gaia 1+2 detection will give a comprehensive theory of the evolution of planetary systems. That's why that is important, and no other technique can compete with Gaia 1+2. So, how do we get that? Well, it must be decided within 5 to 10 years by ESA whether to fly such a mission. And it can only be done in Europe, because only in Europe is the experience to do it, and there is the astrometric community in Europe. We have seen ESA can do it, because after 78 we saw USSR and Russia and USA and also Japan trying to launch an astrometric mission, but they could not get sufficient knowledge and support from the astrophysicists to decide on such things. Only in Europe is this capability. Only in ESA can astrophysicists be convinced. Even the approval of Hipparchus in 1980 was a near miss, as I'll explain a little later. And well, here I say already, the process from 1925 to 1990 depended on 7 persons, which I'll name later. If one of these 7 individuals had been missing, Hipparchus had not been approved in 1980 and probably never, as I'll show in the following. So here is the history of this development. In Copenhagen, an old Norwegian survey from 1861 is shown here. In 1925, Ben Strömgren, who was just 17 years, he had such a great place in the focal plane where stars would cross, and he had a photo cell behind and could record it. So that was the start of photoelectric astrometry. That begins in 1925, began by a teenager, Ben Strömgren, who was became a famous astrophysicist, and is most famous for his astrophysics, but his contribution to astrometry is very unique. He had the plan in 1940 to have a new meridian circle installed in Brofeld. It's 50 kilometers outside Copenhagen, and it was erected there in 1953. So he decided on that as he became director of Copenhagen Observatory, and I was the first student who was asked to work with that instrument. In 1953, I started. So 1953, that's 60 some years hence. And as a soldier, I became familiar with counting techniques, electronic counting techniques, because we counted the fallout from atomic bombs in the dust and rain as soldiers. We should see, the superpowers exploded atomic bombs in the atmosphere, and the dust was spread all over the world, and we could measure it. So I became familiar with electronic counting before any astronomers did so, and that was very important, because in 1958 I moved to Hamburg to learn more, to become an astrophysicist. But in 1960 I had the idea, based on what I have seen, the experiment by Ben Strömgren, that astrometry with photon counting could be done. You see, here slits like Strömgren had, and the star crosses, and then if you count as function of time in small intervals of time, you count how many photons come. Then you can derive the transit time for each of them. Yeah? And much more fainter stars than Strömgren could do with the analog recording techniques. And I also invented that we could have slits inclined, which meant then you could determine whether the star crossed here or down here. So we got the declination component in the focal plane. And that was completely new. And in France, they liked it, and they called it grille de Hog in those years. And this idea I presented in Hamburg, and the director was Otto Heckmann, who became the first general director of ESO. He was immediately convinced that is the thing he needed for an expedition to Australia. And so he got funding for the development already in the course of the 3 months, he got all the funding for it. So thanks that I had the idea in Hamburg, where they needed a technique, and they had Otto Heckmann there. I was lucky to be at the right place with the right idea at the right moment. So we developed it for the region server in Hamburg, and here you see it 6 years later. Took quite some time to do it. Here is the micrometer on the meridian server. Semi-automatic, but recording on punch tapes for a mission to Australia, 67 to 72. And here it is in Hamburg, ready to be sent to Perth. The one person was sitting here with a list of the stars, and she would then set some numbers on toggle switches in this room where she was sitting, and she would call the next star, the declination of the next star. So the person out here would then set the telescope to that direction, and then it would be observed. And in Australia, it was 3 couples. So the husband was standing here, and the wife was sitting in here during the night. And the next day, they got all the punch tapes and reduced it on a computer, which I'll show you. Here is a computer. This is the main building. A computer, it was a transistorized computer, which was very new, and it was the fastest computer in the world, which could be afforded by such a project. It was 10 times faster than the fastest IBM computer, and we purchased it. But if you see what it is able to, here in RAM and what speed it could be, then this computer is 1,000,000 times faster and more capacity than this one. It is in this orders and transistors. And on the punch tape here, the data are punched and read. Yeah. And here is a pavilion in Perth, where the meridian server was located and observed for 5 years. And they could observe 20,000 stars per year. That was fantastic in 1970. Now, in the meantime, the idea of photon counting astrometry had been taken up in France by especially by Pierre Lacroix, who was director of Strasbourg Observatory. Here's his student, Pierre Lacroix, and others in France also worked on astrometry from space, because this old man, he had the idea of doing what we did with the meridian server, to do it with a rotating satellite. And I saw his presentation in 1967. I witnessed it at the IAU assembly in 1967 in Prague. and with other astronomers, and I just shook my head. It's completely unrealistic. So in my eyes, I'm one who know how to design instruments. I could see it's completely unrealistic. But in France, the idea was taken seriously. Good, they did like that. And this gentleman, he was the director of the big observatory in southern France, Jean Cavaleschi. He could see this is a very important idea. And he had it, ESA, he had his, knew how to engage with ESA, so he could make it an ESA project, the space astrometry. And in 1974 it became a European project, and they wanted to start a study, a mission study on space astrometry. And I got a phone call from Paris if I would like to join the group of ESA. And I thought, well, they know that I don't believe it's a good idea, but if they want my advice, I must go. So I went there. And in the morning, we saw that we had also seen this plan before on a group. Here's a beam combiner, which means of 3 parts, which means, if you see it here, it receives light from 2 directions. And then the satellite rotates so that these 2 directions go around and scan the sky in a great circle. That was the basic idea. And to have a very stable beam combiner. Good idea. But how to detect? Well, he wanted to place slits like this and photomultiplier, 1, 2, 3 photomultipliers behind this. And on a smaller telescope here, the path would be like that because it would measure a small circle. And I could see this is not a good idea. And in the afternoon of 14th October 1975, when we had our first meeting, in the afternoon I asked the chairman, which of the ideas of the group do you want us to look at? He had also an idea of a space lab option. And he said, forget what is on the table. Just think of how you can best use space technology for your science. And when I heard that, that relieved me. Then I could think completely freely. And I went back to Copenhagen and started to think about it. And 6 weeks later, I had a number of new ideas how it could be done. First, it should not be 2-dimensional measurement. It should be 1-dimensional, a long scan. And the beam combiner should only have 2 parts. And the angle should not be a multiple of 45 degrees. And there should be a modulating grid. And behind that, an image dissector tube which could measure many stars one after the other. And there should be active attitude control so that we could determine freely the optimum way of scanning the sky. And the optimum way would be the spin axis revolves around the sun at a constant angle. And the star mapper, there will be 1 star mapper with 1 photomultiplier to detect some reference stars and thereby knowing where the telescopes were pointing, and then follow it and the stars of an input catalog of 100,000 stars. These ideas I presented on the 3rd of December, what I had written about in reports, and that is perhaps the best I ever did for astronomy. And half a year later, the telescope of that design looked like this. Just 2 beam combiner with 2 parts, and then reflection into a telescope. And this rotates around an axis like this in a few hours. And in the focal plane, there would be a modulating grid here with 2,000 slits. Look like that for small field here. And the star mapper would detect the stars reference star, so we know how the telescope is pointing, and then one star after the other would be followed by the photocathode, which could be moved electronically and record that star. So several stars would be switched several times of the cathode and measured. So one star at a time would be measured. And that was a principle accepted for impactors. And now let us see how far are we. Well, slits and photon counting, ideas from 1960. Then came Lacroute and Kovalevsky to make it a space project. And then I made a new design in '75. But then we were facing an enormous data reduction problem because 100,000 stars means 5 unknowns for each star, namely position, proper motion, and parallax. That's 5 numbers. So we must derive 5 numbers for the 100,000 stars, 500,000 unknowns, and each star is measured about 100 times during the mission, which means you have millions of condition observation equations and determine 500,000 of unknowns with the least square method. How do you do that? We couldn't see any method. But in 76, in 73, I had met a young student in Lund Observatory, close to Copenhagen. And he had been working with me on some observations from the Earth meridian circle. And I asked him if he would be interested in this data reduction task. And so I had a meeting with him. And 3 weeks later, he sent me a nicely typewritten paper with all the equations which were needed to make the data reduction. He's born in 1950, so he was just 26 when he could do that. Yeah. And another 3 weeks later, he had the simulations, so he could tell what accuracy they would obtain. So that is the speed with Leonard Lindgren was in. The speed he has been working with since then, ever since then, and still today. So he is at the heart of the Gaia project, data reduction. He can do, he says, he's a very modest person, not like me. No, he's very quiet, and but he says if something can be done by mathematics, then it's simple. Yeah, he can just write the formula, and that's how he is. So these are persons, 6 persons. If one of them had not been there, there would have been nobody else to replace him. Then came the studies during 4 years, and in 1980, Hipparchus was approved. But there was one person, if he had not been there, Erik van den Heuvel, in the Astronomy Working Group, it would not have been approved. There would have been no Hipparchus mission. And I have explained that in the report, which I should not tell here. So, and then was Hipparchus flying, 89 to 93, the final results in 97, and the 16 volumes, Tycho 2 in 2000, 2.5 million stars. And well, the Tycho project, how I invented that in 1981, we judged that. And then just return to these 7 key persons from 1925 to 80. They were a chain. Strömgren, myself, what they did, and Lacroute and Kovalevsky. And again, these 7 persons, if they had not, well, I should mention that when Erik van den Heuvel is an astrophysicist, and he was asked by the chairman of the Astronomy Working Group to present the Hipparchus case. And he could see the importance of getting the Hipparcos through better than the astrophysics mission. He was a part of the HUV mission, Van Heuvel and the Jager. And Van Heuvel was able to convince two astrophysicists to vote for Hipparcos. Otherwise, they would have voted for XUV. He was and when Cornelius de Jager understood that, he said, "What are you doing? You are killing your own project." So he had not the ability or the capacity to see it is important to get Hipparcos through. But Van Heuvel, he had. I have not written that story in this history, but every time I meet Van Heuvel, we talk about these days. So the Hipparcos mission flew, and here are the 7 key persons. Ben Strömgren, 3 of them astrophysicists, and without them there would have been no Hipparcos mission. Now, 2 Gaia-like missions. Only ESA and astrophysicists can decide, and it must be fly in 20 to 30 years. That means approval must be done within 5 or 10 years to do it. And I'm working on that, and I've written a lot about it in a report called Absolute Astrometry in the Next 50 Years, where the input from my colleagues here have been very important. And now let us look at the astrometric physics and the top science which can be obtained from a new Gaia-like mission versus what is obtained from a single Gaia mission. Well, imaging of radio-optical sources need positions, say 50 years from now, what will be the positions extrapolated from the Gaia? They would be, if we have a second Gaia mission, would be 10, 20 times more accurate. And it's important to have very accurate reference system for radio astronomers, because they measure their objects, quasars and so on, in an absolute reference system. But they want to refer it to the optical image, which means they might need to have optical reference positions and radio positions in a very high accuracy. And in order to superpose the image, the optical image with the radio image. And therefore they need positions of radio sources. And the dynamics of dark matter from stellar probe motion, tangential velocities can be obtained with 10 times smaller errors in a 30 times larger volume with 2 Gaia-like missions. Stellar distances in 3 times larger volume. Exoplanets, as I explained, up to 40 years, where Gaia can only determine up to 10 years. And quasars, by only 0 motions, can be determined in 100 times cleaner samples from 2 missions. And solar system observations from 2 missions will give much better orbits and asteroid masses. And astrometry and photometry with a 10th of an arc-second resolution is very useful. And astrometric binaries will be obtained, common proper motion pairs, and so on and so on. And that's the end of my talk. Thank you for your attention. Please, I hope you have
Any questions?
remarks or questions.
That is not a question because everything was very clear.
Thank you.
So thank you, Erik. Thank you very much. Do you have any questions or comments to the people?
If I have a
Do
question.
you have any questions or comments?
Well, if you would read this take a look at this paper and send me your comments. It would be nice.
So, to your knowledge, is there any group working on seriously for the successor for Gaia, or just ideas? What you mentioned here.
This idea of a Gaia successor.
Yeah.
Yeah. Only me. No, because
for
all the
instance,
others.
Lindegren or his colleagues.
Well, Lindegren, when he heard that I would submit such a proposal 2 years ago, he said, "Absolutely, you must submit it." And but there were others.
Yeah.
Very high-standing person who said, "You should never have submitted it. No, that should be submitted by a committee." But I did it just by myself, and had comments. I sent the draft out one day, and had the comments the next day, and I had only 8 days to write the proposal. Others knew about it a longer time. So I have been gifted with being. I can still be fascinated and work hard, and also thanks to my wife, she let me do everything of that kind, and so I had a lucky time. But there will be a meeting in Cambridge in beginning of July by invitation of I think 30 people have been invited to that, where we'll discuss these options. But the others submitted before me. There was a group led by the science team of Gaia. We submitted a proposal to do much higher accuracy, nanoarc second accuracy, and also, if possible, should be in the infrared, so they could penetrate into the bulge. But no instrument idea. They didn't have time to it, and still 2 years after, there are no instrument ideas. Whereas I think you must have an idea how to make an instrument. Otherwise, it's just, well, wishful thinking, as we say, which is important to do, but there must come concrete proposal for it.
But isn't it also premature a little bit before? Isn't it also premature a little bit before having played with the Gaia's results, right?
No, not at all.
Not at all?
No, because if you know what the results will be, then you can predict then you can think about the science cases for it. So, I mean, here in this case, I put up all these science
It must be
cases.
hard to convince the community, right? No? I mean, they would say...
Yeah, some of them.
Yeah,
yes,
they would say, let's play with Gaia then.
Yes, some will do. But there will be people who have the foresight, who can see it is necessary. If it is not done, then high accuracy astrometry will die. That's also an argument, that it must be done within 20, 30 years, when the experience is still there. Because, you see, astrophysical projects, they have a much broader appeal to people. So they can be engaged in ideas about astrophysical projects, whereas astrometric projects requires a different mind to get interested in it. And the experience will be lost if it is not nurtured by a big mission. And then you cannot revive this, because to fly a mission requires many people. Bright people, some very bright in something, others in other things, but it requires hundreds of people. And if they have been working with astrophysics, they will stay with astrophysics. That's very important and interesting. You cannot gather hundreds of people around an astrometry mission if you don't do it within 10 or 20 years. And only in Europe. You cannot do it in America. Also, American colleagues said to me, you can convince a congressman that it is important to detect planets around other stars. But you cannot convince a congressman that it's important to measure the positions and motion of 100,000 stars.
Politicians are the same.
Huh?
Politicians are the same. All over.
Okay, perhaps, yeah, yeah, more or less. But anyway, this was an American colleague who said that to me. Yes. Yes.
Well, thank you. Thank you very much.
You now, Gaia Mission results and the prospects review. Okay. And it is divided like
Isn't it good? Sinan,
then I must question.
Sinan, bunu demek
No,
istiyorum.
I not switch.
This must be.
But I can use this. Yes, now it comes. Yes, now it comes. Thank you very much. So, first part is the Gaia mission and how it performs and the science you get from it. The next part are about long period exoplanets, how they can be determined by astrometry, detected by astrometry, and about a Gaia successor, which only ESA can do and which must fly in 20 to 30 years. That's what I'm working on. So first, about astrometry. Astrometry is about positions, proper.
To give a seminar. Normally, I don't do a long speech before seminar, but this talk deserves a few more words for our students, especially. I collected some information about Erik. Let me summarize it. Erik is responsible for many of the innovative techniques employed in the Hipparcos and Gaia missions. He proposed in 1975 a new design of a scanning astrometric mission, which became Hipparcos. In 1992, he proposed an astrometric mission with CCDs in time-delayed integration, which became Gaia. Erik published the following catalog with his colleagues in 2000, the Tycho II catalog of the 2.5 million brightest stars, which has been one of the most important catalogs in astronomy. Erik received the ESA Director of Science Medal for outstanding contribution to the science program in 1999. The International Astronomical Union gave the name Erik Hog to an asteroid. This drew a medal from Russia awarded in 2009. Although Erik has been formally retired, he is still contributing Gaia mission with his papers. Erik's papers are kept and registered in the Royal Library near Copenhagen. Thank you, Erik, for being here with us.
Motions and parallaxes of stars to determine them to the best possible accuracy. And there is absolute astrometry, which means astrometry of positions all over the sky connected in a good coordinate system. Then there is relative astrometry, which you can make in a telescope with a small field. Yeah? And all sky astrometry is really the all sky and the small field astrometry. So what I'm talking about today is only absolute all sky astrometry, not the other small field, which is also important, but not the subject of today. And absolute astrometry was done for 300 years, was done mainly by meridian circle. Here's a meridian circle, a telescope on a horizontal east-west axis, And you observe a star when it crosses the field of view, observe the transit time, and the inclination of the telescope gives a declination. That is meridian astrometry. But in 1989, we launched a satellite which could do absolute astrometry much more accurately. The Hipparcos satellite by ESA, which you see here. And in 2013, we launched the Gaia satellite, which you see here. And the question is then, what is the future for all sky astrometry? After Gaia, what must come after?
Let us listen.
Thank you for the very invitation to come here and for the nice welcome we have received. I should tell you that about half a year ago, when I was working on Gaia Mission in 20 years, I saw a paper by Tansel and Selçuk about calibration of absolute magnitude. And I had some questions that I wrote to them, and I got immediate answer. Then there was something I did not understand because I don't know everything, so I had to ask, and they answered immediately. And also when there were further questions, they answered immediately. This is not so often that you get immediate, very useful answers from colleagues. I'm very grateful for that. And so I said to my wife a few months ago, don't you think this is the time we should go and see Istanbul? I was in Istanbul alone with a group 3 years ago, and I said, when I came home, we must go there to see all these things. So, and this is the time. So I wrote to Tansel and Selçuk if they would like to have a talk. And they immediately answered yes, and that's why I'm here. So I'm presenting Gaia. That's what I'm working on. So a Gaia successor is needed by 2033. That's what I'm trying to convince you of. And the Gaia measurement principle is shown here. You see, here's the satellite, and the spin axis means that the two telescopes on board will observe stars on a great circle. Along the great circle, they measure. And then the spin axis is turned a little all the time, so that the next circle will be a little bit tilted. And the measurements are done by the stars coming into the field, and in 20 seconds about, they go across the field. First they are measured astrometrically. First they are detected. All stars to 20th magnitude are detected and then measured in the remaining part of the field. And then they are measured photometrically and then spectroscopically the brighter ones. And the resolution is 1/10 of an arc second, which is comparable to the resolution of Hubble Space Telescope. It will map the entire sky with this detail to 20th magnitude, which means 1 billion stars. And here's the first image we got from Gaia in February 2014 of a globular cluster in the LMC, just 3